In this video, I'll be working on the following setup. Figure 240 in your process control manual. So I'll be controlling the level of water in the column, and I'll be doing that by manipulating the pneumatic control valve. The level of the water will be measured with the differential pressure transmitter, the one that you see here in the figure. The electrical connection for this experiment is the following one. That's figure 241. I have eliminated the recorder. I will be adding it in a different experiment. So I have the PLC, which is the LIC, connected to my pneumatic control valve. So the output of the PLC will be connected to my pneumatic control valve, and the input of my PLC will be connected to my LIT, which is my differential pressure indicator. This is how the experiment looks like. The differential pressure indicator has been configured so that the minimum value, so 4 milliamp, it will send 4 milliamp to my PLC when the column is fully empty. So the water is at approximately level 0. And when it is 75 centimeters high, so when the level of the water is 75 meters high, then the differential pressure indicator will send a 20 milliamp signal to my PLC. So I am manipulating, so what is being controlled? What is being controlled is the level of water. What is being manipulated is the input flow of water in my column. So I am doing the manipulation by controlling the pneumatic control valve position. The pump is operating at approximately 50 hertz. So the pump is operating at approximately 50 hertz, not exactly 50 hertz, but close to it. And in this setup, the top of the column is not pressurized. That would make a difference if it was pressurized. So it's important to know that this column is not pressurized. And it is connected, so the top of the column, one of the outlets is connected to hand valve number 3, which is open. And I also have fully open hand valve 4 and hand valve 5, which is slightly different setup than the one suggested by the experiment in figure 240. The only difference is that I don't have a solenoid valve. I decided to eliminate it and simply to connect the bottom of my column to hand valve 4 and 5 with tubes. It does not change anything to the experiment. So because the pump in this experiment is working much harder than in a previous experiment where I had it at 30 hertz, so I need to open these two valves to allow the water. So this would prevent the water from overflowing. Otherwise, the water may overflow and probably be harder to stabilize it. So right now, as I said earlier, this is not a pressurized column. If it was pressurized, the pump would have a hard time. Well, it would be working harder in order to raise the level of water in the column, because it would be a pressurized column. But since this is not a pressurized column, the pressure at the top of the column is in equilibrium with the pressure of the air. Therefore, at the top of the column, we have it is equal to the air pressure. So in this experiment, I will be automatically controlling the level of the water in the column. And to do that, there are different techniques, and I will be using the proportional derivative integral, as well as the PID, which is proportional integral derivative. So I'll start with the proportional, and I'll follow the suggestions provided by your book. So I'll start with the P. So this is in figure 225. And I'll start with a small p. So if I take a look, I have disabled the derivative and integral, and I've started with the p with a small value, and I've started with 1. I'll set this to 50. Set this to 50 as my initial value, and just set this to 1. So these are my initial values, and of course these values you can change them as you like. So I have 1 for P. P is enabled, TI and TD are disabled. So this is P control, and what I have right now is 50% set point. So I have set the set point to 50%. My process value is at 85.74. What I will do, since my process value is stable, what I will do is I will, so you can see that here, it's the green line, and you can also see that here, it's stable, it's not changing at all actually. And it's true that the level of water is not changing at all. So what I'm going to do right now, I'm going to do a set point change to see how my P does, how it reacts to a change in set point. Change it to 70%. So we notice that the water is rising a little bit. So because the value of the P is small, I don't expect the system to be able to reach actually 70. There will be an offset. The water looks like it's going to stabilize soon, so there will be an offset between 70 and my set point. Well, the set point and the process variable. Looks like very close to settling. We'll take a look. So obviously this takes time. It's time consuming to do this type of tuning. So I'm almost at the maximum value. Remember, the maximum value is not what's shown here. It's not 92 centimeters. My maximum value is actually 75. So I'm very close to 75. Get the reading here. So I'm not getting oscillations. I don't see oscillations. I don't see that in the trend. If I make a close-up, I don't see any oscillations. It's actually a straight line, and I can also see that right here. So it's not oscillating. So since it's not oscillating, and if I take a look at what is suggested in your book, it says, is the process response underdamped and oscillatory? No. So I'll increase again the gain. Increase the gain. Increase it to 2 this time. Double. And I'll change my set point once again to 50%. I'll have to wait and see what happens. Because you can see the water level dropping. Of course there will be an offset. I expect an offset between the process variable and the set point. I don't expect it to reach exactly 50. You can see the reading here as well. It looks like it has stabilized. Just going to go back. So I'm not getting any oscillations. No oscillations. So the green line is straight. We can look at the trend here without the close-up. It's straight. There is an offset, very obvious offset between the green and the blue, the set point and the process variable. So what I'm going to do, I'm going to again double it. I may get oscillations this time. I'm going to change the set point again, see how it reacts. The water is rising. So it's rising, getting close to 70. Moving very slow. This is a little bit strange. I see 78.72%. 78.72. Okay, no, this is okay. This is okay. So it is above the set point. That is correct. It is above the set point. It's not strange. I'm confusing percentage with centimeters. So this is actually centimeters. Whereas the reading on the HMI, it's percentage of the span from 0 to 75. So 75 centimeters. So I don't see any oscillations. I don't see it here. I see an offset. And I don't see it here in the close-up either. So there is an obvious offset, no oscillations. And so because of that, I will again double the value, and I will change the set point to 50%. Water level is dropping to reach my set point, and now I feel that we're probably going to get oscillation. Now it rose again. So it looks, from the look and feel, we will probably get some oscillations, but again, I'm not sure. The readings are in centimeters, and you also have a bar below the centimeter that shows you the how empty or how full the column is. So the black part of the bar is how full. The full part of the column, and the white bars are the empty portion of the span. So this represents the span. The bar below the reading, centimeter reading, represents the span of the water in the column. It looks like no, we probably did not get no oscillations actually. Nope. I thought we probably were going to get oscillations. No oscillations. There is an offset. There's a small offset, but no oscillations. So what I will do, double again. I will have to double again. I don't have to, but that's what your manual suggests. So I'll go with what the manual is saying and see how the system reacts. So the water is rising to reach 70%. So 70% of 75 centimeters can be calculated, obviously. So the 70% here represents 70% of the span, which is 75 centimeters of water. So that the head of the water, or I should say the maximum level of the water is 75 centimeters, and 70% would be 70% of 75 centimeters, which is slightly less than, well, less than 70 centimeters. So again, I am very close, but I'm very close. So there is an offset. but no oscillations still. No oscillations. No oscillations. The green is straight. So despite the fact that the controller is oscillating, right? I should say the pneumatic control valve is oscillating, but I don't see much. I mean, there is variation. The proportional value, sorry, the process value is varying slightly, but not enough to show us any oscillations. So what I'm going to do, I'm going to increase it to 32. Maybe this time I'll get oscillations. So double 16 to 32, and maybe this time get oscillations. Water is going down. %50 of 75 is approximately 37. Maybe this time we'll get a little bit of oscillation. We have to wait and see. Okay, let's take a look. Not too sure if this is going to oscillate or not. There's a little bit of oscillations, that's for sure. So if this continues, I am not, so we can probably see it even clearer here. We already had a little bit of oscillation with 16. It's just a little bit. But here it's a little bit more evident when we look at the graph. So if we look at the water level, it's oscillating a little bit. So we can see the oscillations. So what I'm going to do, I'm going to reduce, because your manual says to reduce it between, once you see oscillations, reduce it between the current value, so a value right in between 16 and 32. Between 16 and 32, there is 16 units. So 8 plus 16, because half of 16 is 8, and 8 plus 16 would be 24. So I'm going to reduce it to 24, and I'll stop there for proportion. 24, and that's it. So I'm not going to make a set point change, but now what I'm going to be doing, I'm going to bring in the integral portion. So the integral portion, I could start with 99 or a little bit maybe higher, but I know I can't get it to 100. But I decided to start at 50. That's what I did last time in the previous video, and so I'll start at 50 and see what it gives me. If it doesn't give me good results, then I can start again. But I'll start with 50, so I'll start by enabling it, and I'll make a set point change. Set point change is arbitrary. You can change to 40%, 30, 20, 10, 5, 95, whatever you like. But I'm moving between 50 and 70 because it's a little bit less time consuming. because I am recording. So the water is going up, and it's slowly getting closer, I should say, to my set point. So given I have an intergrowth, it should correct my offset, but not necessarily, because you need to continuously, you need to properly, that is, tune it to get it to eliminate the offset. I'm very close to the set point. And I'm not getting any oscillations. I'm very, very, very close, and I'm not getting any oscillations. Well, actually, maybe I am. Small oscillations. Usually when the manipulated variable is oscillating, usually you'll get oscillations in your controlled variable as well. So yes, it is oscillating. So let's just take a look at what your manual says. So once you bring in, is the process response underdamped? Yes. So in this case, I don't have an actual previous value. So I may have to say no, just to see what I get. So I'll decrease it by a factor of 2. So I am getting a little bit of oscillations. I mean, it is obvious. So I could leave it like this, but I'll just for the sake of experimenting, I'll cut it in 2. Cut the value in 2 and see if I get better response. So I'm going to have to wait a little bit and see what happens. If I had oscillations previously, I assume that my oscillations are going to become more evident this time. So 50% of 75 is approximately 37.5. Well, it is 37.5 centimeters. So I'm oscillating. The water is oscillating around that value. Not too far, very, very close. But I am getting oscillations. And so what I will do, because of these small oscillations, what I will do is cut the number, set the value for the integral between 50 and 25. So there's 25 units between, or seconds in this case, 25 seconds between 50 seconds and 25. So half of that is 12.5. So I will set it, I'll put a integer number instead of a decimal. So I will put it at, I will add to that number 13. So 13, that makes it 30, so 30, 35, 38. So 38. And I'm not going to make any set point change. I will leave it like that. And what I will do now is bring in the integral. So now this is PI control. So initially I started with the P control. Once it started to oscillate, I did what I had to do. So I had to do some math, and I enabled the integral. So now I have PI control, and with PI control, this is what I get. A little bit of oscillation, very, very close to the set point. The controller is oscillating. So let's see if I can get something better than this, and hopefully to reduce the oscillation, because that will make my controller work less harder and will be less hard on the equipment, on the system itself. So what I'm going to do right now is I'm going to bring in the integral, and I'll enable it. Still have oscillations. I need to of course change the set point. So of course, my hope is to reduce oscillations, and of course try to have the process variable as close as possible to my set point with minimal oscillations. We can see here the big waves of the controller. So it's oscillating. Obviously, since it's oscillating, the control variable will also oscillate. So level will also oscillate a little bit. So I still have oscillations. What I will do right now is just going to go back to the book and see what it says. It says, is the process taking longer? And if there is overshoot. So, no, I don't think so. So what I'll do is I will increase the value by 2. Value by 2, make a set point change. So we can see the process variable is trying to catch up to set point. See that here. See the rise. So this would be called underdamped. This curve is underdamped. The green one is underdamped. still oscillations. You can see the oscillations right here. A little bit. So what I will do is I will increase the value again. And again change the set point. It looks like this time it took less time to reach. Took less time to reach, but again, I can't conclude too early. Have to wait and see. Just gonna have to see if it suggests doubling or. Okay, so here it suggests 4 times, so I'll increase it by 4, and the water level is rising. So if this continues to oscillate, my intention is to go back to the integral and bring it back to 50. That's my intention, but I have to wait and see if I still get oscillations, and see if I can tune those values, adjust them to get a better response from my process control variable. So it's true that the controller is working harder. I mean, it's oscillating, not necessarily working harder. It continues to oscillate. Just want to see what I had before. Is it oscillating more? I don't think. It was between 20 and 40. So like this, you can investigate what happened. So if I look here, if I look here, it's oscillating between approximately 20 and 40. If you look at the scale, it's oscillating between 20 and 40. And I can go back in time by pressing this, kind of rewinding, and taking a look if the oscillation was worse before when I started. But yeah, the oscillation was maybe a little bit bigger. And so if I look now, maybe it reduced by a little bit. So I am at set point right now. Very, very close to it. And although it's true that the pneumatic control valve is oscillating, but my process variable is very close to my set point. What I would like to do right now is just to check if by changing the TI to 50, if I will get anything better. So I'll change it to 50. I'll make a set point change and see if the oscillations of my pneumatic control valve does go down. Of course, we have to wait and see what happens. I think the oscillations, well, at least for now, it looks like it's a little bit worse. But that doesn't mean it's going to stay like that. I don't see much of a change. I don't see much of a change actually. Take it back to 38, which is what I had earlier. So I put the set point to 85 just to experiment and see how well it works. So this is part of fine-tuning your algorithm to see if you can get a better response. very stable. Actually, I have less, if you have noticed, I have less oscillations. My oscillations were between 20 and 40, and sometimes surpassing, but now I see that I have less oscillations. And this is good news, of course, for my controller. So my pneumatic control valve is working less hard, which is a good thing. And so I'm kind of fine-tuning right now. I'm actually fine-tuning and testing at the same time. So I brought it all the way down to 25%. The water level is going down. Yep, it looks like I have reached my set point. Very close. And the pneumatic control valve, I think, is working less hard. If we go back and take a look at this, it's working harder. You can see here the scale 20 to 40. And let's compare it to now. Take a look. Just have to wait for it to stabilize before we can conclude if it's working less hard or not. For the segment here, it looked like it was working less hard. But here, it looks like it's working pretty hard. Maybe nothing has changed in terms of how much it's oscillating. But the set point, we're very close to the set point. So the integral will slow down the response. So what I have noticed is that it takes time to stabilize, and as time progresses, it seems that that the pneumatic control valve is working a little bit less hard, but I can't just can't conclude that, but probably not. We'd have to just go back in time and see. I think it is. So if we look here, and if we look it's probably not working. No, it's probably the same. It's probably the same. Nevertheless, there's no oscillation for my set point. Set point, the process variable. Of course, there is variations, but very, very little. Very, very little. Of course, ideally, the pneumatic control valve should be not oscillating, or very little oscillating. That would be the ideal situation. To achieve that, I would have to do some tuning to achieve that level of control. But that would, of course, take time. So I will end my video with this. So the process variable is very close to the set point. And the problem here is that the control valve is oscillating, as we can see here.